Hello everyone, welcome to GATE Pass. In this video, I am going to take problems that were related to thermodynamics and which appeared in year 2016. So there were in all 5 problems. I am going to take 3 problems in this video. So the first problem which I am going to take is question number 5, and it gives you the partial molar enthalpy in kilojoules per mole as a function of x1 and x2. x1 and x2, these are nothing but the mole fractions of species 1 and species 2. Okay, now they have asked you to calculate the partial molar enthalpy of species I at infinite dilution. Okay, so when you say infinite dilution of species 1, what you mean is that your x1 tends to 0 and your x2 tends to 1. Okay. So, at infinite dilution, since you have been directly given the relation of partial molar enthalpy for species 1, so it was a very straightforward question. It's hardly going to take us half a minute to solve it. So, h1 bar infinity, that is at infinite dilution, that will be equal to, you have to just put these values over here. So, when I put x1 equal to 0, and x2 equal to 1, so this term will go to 0 because x1 is 0, x2 is 1, so I am left with 2 minus 60, that is equal to minus 58, and it will be kilojoules per mole. So this was the answer. So the second problem which I am going to take is question number 11. This problem is based on Raoult's law. So you will observe that every year there is one problem which is either based on Henry's law or Raoult's law. So I will ask you to go and watch one of my videos in which I have derived Henry's law and Raoult's law from the first principle and told you where to use Henry's law and where to use your Raoult's law. Okay, so in this problem statement they have directly told you that the mixture follows Raoult's law. Okay, so let's first see the problem description. There is a binary mixture of benzene and toluene at 350 Kelvin. The mole fraction of benzene is given, so it is given as 0.2. So directly you can write what will be the mole fraction of toluene. It will be 1 minus 0.2, that is 0.8. The vapor pressure of benzene and that of toluene at 350 Kelvin, they are given. So I also refer to them as my saturation pressures. The vapor phase is in contact with the liquid mixture and it is in equilibrium with it, and you have to calculate what is the mole fraction of benzene in the vapor phase. So it's very simple problem because there is Raoult's law, no non-ideality, so I can directly write my Raoult's law for both the components. So if I write YB P, that is equal to XB P saturation, where P is your total pressure. Okay. Similarly, for toluene, I can write the same equation. Okay. Now, I have told you that if you have a mixture which consists of two very closely related species, like over here say benzene and toluene, okay, they are chemically very similar, then you can apply Raoult's law for all the concentrations. Okay. So, now I have written my Raoult's law for benzene as well as toluene. I have to find YB, so I will use this equation, but however the total pressure is not given. So first I will have to find total pressure using these equations. So what I will do is I will add this equation and this equation. Okay. So what I get is that YB plus YT multiplied with P, that is equal to XB PB sat plus XT, it is XT, plus XT PT sat. Okay. Now YB plus YT, okay, that is equal to 1 because you have only 2 components. The summation of mole fraction will be 1. So this thing goes to 1. So you are left with only pressure. So the pressure value is given by this. Now I will put the value of pressure in this equation. So what I get is that my mole fraction will be equal to XB PV sat divided by pressure. Pressure is nothing but this thing. So I am going to write it over here. Okay. Now put the values. Okay. If you cannot see, I will write it over here. So my YB, that is equal to XB is 0.2, PB is 92. That thing divided by 0.2 into 92 plus 0.8 into 35. Do this calculation and you will directly get the answer for the mole fraction, which comes out to be 0.396. In the question they have asked you to report this up to 2 decimal places. So round it off to 2 decimal places. You can write it as 0.40. Okay, so that's the answer. So the third problem which I am going to take is question number 34. It again appeared for 2 marks. This question is very simple. It is based on excess Gibbs free energy. So let's first go through the problem statement. So there is a binary solution of species 1 and 2, with the species 1 having a mole fraction of 0.4. So the species 2 will have a mole fraction of 0.6. Okay. Now they have given that molar excess Gibbs free energy divided by RT, that is given by this equation 3x1 x2. Further they have given that if G1 and G2 are the molar Gibbs free energy of pure species 1 and 2, then they have given you the value of G1 by RT and G2 by RT. With this information you have to calculate your G by RT, and your G by RT is, G is basically Gibbs free energy of the mixture at same temperature. Okay. Let's first see how are you going to calculate this. So you have been given GE by RT. Since I know what are x1 and x2, so I can quickly calculate this value. So it will be 3 into 0.4 into 0.6. So the value which comes out is 0.72. So I have the value of GE by RT. Now let's write down the definition of GE by RT. What is it? It is the deviation from the ideal solution. Okay, so that means that is equal to G by RT minus G of ideal solution by RT. Okay, so over here your G is the Gibbs free energy of the mixture at same temperature, and GID is the Gibbs free energy of the ideal mixture. So this is how you define your excess, molar excess Gibbs free energy. Fine. Since I have to find out this value over here, so what I will do is I will rearrange this. So I get the equation G by RT, that is equal to GE by RT plus GID by RT. Okay, this thing you have already calculated. Now you have to find out what will be your molar Gibbs free energy for the ideal solution. I have already taught you the ideal solution model in one of my previous videos. I think it was GATE 2022. So you can go, if you have not seen that video, go and watch that video so that ideal solution model is clear to you. So from ideal solution model, GI, okay, for an ideal solution. So what I am writing over here is my partial molar Gibbs free energy of species I in an ideal solution, that is equal to GI plus RT ln Xi. Okay, so from that I can estimate my mixture property by applying summability relation. So I will get my GID, that will be equal to summation over all I Xi GI. Okay, so this is my summability relation. So from this equation I am going to find out my molar Gibbs free energy for the ideal solution by applying summability. So it will be summation over all I Xi GI plus RT summation over all I Xi ln Xi. Okay, now since the values of G by RT are given, so I am going to divide this whole equation by RT and this RT will go away. Okay, now plug in the values in order to find out your GID by RT. So my Xi, so for the first component x1 is 0.4, G1 by RT is given, that is 1, plus for second component x2 is 0.6 and G2 by RT is given as 2, plus now do this summation Xi ln Xi, so 0.4 ln of 0.4 plus 0.6 ln of 0.6. Now evaluate this, and when you do the calculation, your answer is 0.926. What we have evaluated is the Gibbs free energy of the ideal solution at same temperature and pressure divided by RT. So this term we have evaluated. Now in order to calculate your Gibbs free energy per mole of the solution, okay, you have to just add this plus this. So this you have calculated already over here, that is equal to 0.72, and GID by RT is 0.926, and the value which you get is 1.646. So they have asked you to round it off to 2 decimal places, so it will be 1.65. So that's your final answer. So I hope that you understood the problems, and please don't forget to like my video and subscribe to my channel, and thanks for watching.